Hi, thank you so much for tuning into this talk, which is part of the IEEE APS 2020 session, Emerging Technologies in Biomedicine. My name is Caitlin Hall. I am an undergraduate researcher here at the University of Utah. I have been studying implanted antenna technology for the past 4 years, and I am so excited to be able to share this talk with you today. Not least of all because this work represents a collaboration not only across departments here at the University of Utah, between the electrical engineering department and the chemical engineering department, but also a collaboration across institutions, that is between the University of Utah and the University of Wisconsin at Madison. I am so honored to have been able to collaborate with all of these people, and I am thrilled to be able to share my talk, Adaptation of a Microwave Ablation System for Wireless Medical Applications, with you today. So let's get started. It will come as no surprise to anyone participating in this session that it is a very exciting time in the implantable antenna industry. And that is because there are thousands of implanted medical devices which perform functions such as sensing, stimulation, and drug delivery, and these perform essential medical care functions for millions of people. But even more fundamental than that is, from an engineering perspective, it is also very exciting to be an implantable antenna engineer right now. And that is because these implants are continuing to shrink. We can see in this figure to the right here that it used to be similar to this Medtronic pacemaker, which is on the order of centimeters, but continued advancements in the implant industry has led to even smaller implants, such as this glucose sensor the size of a coin, and even smaller, such as this deep brain stimulator that is less than the size of a thumbnail. Now, this is very exciting, but of course this poses some new engineering challenges. I would like to discuss two main ones here. So the first is that as these implants continue to shrink, we can no longer use conventional antennas. And by that I mean that miniaturization efforts of these antennas can only take us so far. At a certain point, there is a necessary shift upward in frequency as an antenna becomes so small. This is not ideal, not only because it shifts us away from the medical implant communication system band at 406 megahertz, but also because there comes some power deposition, or rather power absorption issues at higher frequencies that make it difficult to deliver the necessary power to these devices in order to perform telemetry. The solution that we propose is using a focusing lens antenna to direct needed energy down onto the implant. As you can see to the figure at the right, this is constructed of two rods that are conductive, and they constructively couple energy down in sort of a lens focusing pattern right in this central area between these two rods, ideally where the implanted medical device would be located. These fields concentrate on tips and in gaps. And also, as I mentioned, constructive coupling occurs to create this focused lens of energy directly down onto an implanted medical device, which allows it to receive the necessary amount of power. The second concern, which I alluded to earlier, is that the human body creates challenges for adequate power deposition. This is especially true at higher frequencies, but this is not a new problem in the implanted medical device industry. The human body is a non-ideal place for antennas to be due to its attenuating of antennas and other challenges associated with the human body. Our proposal is to 3D print this focusing lens antenna that we've proposed directly into the body using a biocompatible polymer gel. This material is liquid at room temperature but solidifies when heated. This means that it can be injected directly into the body, and as it is injected, heated to create this solid but flexible material. So the solidified material becomes flexible and currently semiconductive, but in the future conductive. This is ideal both because the flexibility helps deal with some of the otherwise scar tissue that would form that can cause attenuation. And also the conductive rods create that constructive coupling, as we discussed. So the main takeaway is this: 3D printing in the body is an emerging technology for a host of applications, including wireless telemetry. Really, this emerging technology comes from two well-established technologies within the biomedical community. The first is microwave ablation, and the second is polymer-based drug delivery. When we combine these two technologies, we get what you see on the right, which is this 3D printing system where you inject the microwave ablation applicator, inject your polymer, and then as you heat, you undergo this solidifying process and you can print these rods directly into the body. Now, right now, this technology is only a concept within the author's own minds. And so the purpose of this talk is both to discuss the two contributing technologies, microwave ablation and thermally activated biopolymer, but then also, if the year 2020 has taught us anything, it is that the scientific process can be summed up as testing, testing, testing. And so at the end of this talk, we will discuss some of the tests that we engaged in order to better understand this potential technology and how it will function. But speaking of 2020 and testing, 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 I feel this graphic is a little out of date. So let's make a quick update before we continue. That's better. Now let's start with the first contributing technology, microwave ablation. Microwave ablation comes from a cancer treatment wherein a microwave applicator, as you can see in this figure to the left, is injected directly into the tissue around a tumor site, and then the tumor cells are heated to cytotoxic or dangerous levels, killing off the tumor cells. Microwave ablation is typically used for tumor cells between 3 and 5 centimeters in diameter. And so as a result, these microwave ablation applicators are often coaxial in design. We can see the three most common designs in the figure on the right, which are triaxial, slotted, or choked designs. These designs produce a concentrated area of heating around the tumor designed to heat only the tumor and not surrounding healthy tissue. This is ideal for our purposes in 3D printing in the body because they provide this concentrated heating to a very localized area. Specifically, they provide a spherical heating pattern concentrated at the tip, and the coaxial design makes for easy insertion and injection. Within these tests that we will discuss towards the end of this talk, we focused on this antenna design shown in this red box, which is a design by our colleagues at the University of Wisconsin-Madison. All right, so now we have the second technology, this thermally activated biopolymer. So a thermally activated biopolymer is exactly what it sounds like. It is fluid below a certain temperature, and then when heated, it undergoes chemical cross-linking to become a solid permanently when it raises above 40 degrees Celsius. Now at the molecular level, we have a polymer chain thermosensitive capsule. The thermosensitive capsules encapsulate this chemical cross-linker material that I'm talking about. When heated, these capsules break open and mix with these polymer chains, initiating this chemical process that results in this solidified gel-like material. But let's make that a little bit more clear. So if we zoom in on the biopolymer to a molecular level and we begin heating, we see as the heating breaks open these liposomes, they begin to mix with the polymer chain. And as they continue to mix, they undergo this chemical process and solidify until they've reached this gel-like state. Let's see that one more time. So we zoom in. We have at a molecular level this heating breaking open these liposomes. They mix with those blue squiggly-like polymer chains and then become this gel-like solidified substance. Let's see this in action for real with this video. So we can see this RFCA probe, which is heating a beaker of polymer, and at the end of that probe, we have this solidified sphere of cross-linked material. While RFCA, or radiofrequency catheter ablation, is a good testing point, it is not sufficient for our applications where we want to actually inject and heat at the same time. Now let's look a little bit more closely at the dielectric properties of this polymer. So currently, I want you to focus most of all on the conductivity. So we can see currently our conductivity levels are on the order of about 10 Siemens per meter. But as we can see from the figure on the right, which looks at the SAR power deposition for those implanted rod antennas at different insertion depths, we need a conductivity more on the order of 10 to the third or 10 to the fourth Siemens per meter. So while we are not currently at that level of conductivity yet with our biopolymer, we are quite optimistic that we will get there. And as we get to our target level conductivities, heating precision will only improve. So while we are at a less than ideal conductivity currently, that less than ideal conductivity gives us a worst case scenario in terms of the precision of our 3D printing system. So now the part you've been waiting for: testing, testing, and more testing. Specifically, we used our colleague's antenna at the University of Wisconsin. This is a 10 gigahertz floating sleeve dipole antenna, and we tested it in two different environments. The first is in egg white, and then the second was a small vial of biopolymer surrounded by salt water in order to minimize the amount of reflections because we had such a small amount of this biopolymer available. In the first test, the pulsed magnetrod generator was used to deliver an average power of 20 watts over 2 minutes to the egg white. We chose egg white both because we can see the ablation, if you will, as the egg white turns to this kind of white meringue, but also because the thermal properties of egg white are relatively similar to those of the biopolymer. So let's see this in action. Watching this video, we can see this area of ablation developing on the antenna. Now again, for 3D printing, we would need concentrated heating at the tip, but this was a good jumping off point for us to establish microwave ablation as feasible for this 3D printing concept. And we can see at the end of this 2 minutes at an average power of 20 watts, we get this almost spherical, fairly large ablation area, which is exactly what we would hope for. When it comes to the biopolymer, we actually instituted two separate tests, and were able to successfully cross-link the biopolymer after 15 minutes of heating at an average power of 15 watts. So on the figure, we can see the thermal properties of the biopolymer, which again are extremely similar to those of egg white. And we can see a small area of solidified biopolymer material. However, the overall ablated or cross-linked area is much higher than this would suggest, as you'll see in these figures. So this is comparing two different trials. We can see that while both of these tests got well above the cross-linking temperature of 40 degrees Celsius relatively quickly in less than a minute, only the longer duration test was successful. This is likely due to the amount of time that it takes for the chemical cross-linking to occur. We can see that the entire, or nearly the entire, vial of biopolymer was successfully cross-linked in this 15-minute period. Meanwhile, this shorter one was not successful. And so this leads us to our future work. While this floating sleeve dipole antenna at 10 gigahertz showed us that it is more than feasible to heat the biopolymer using this microwave ablation technology, the next step will be to transition it to an ISM frequency such as 2.45 gigahertz. And so the future work will focus on being able to test in an environment like egg white, which is very similar from a thermal point of view to the biopolymer. I wanted to thank both our collaborators at the University of Wisconsin specifically Dr. Susan Hagnes and her graduate student Audrey Evans. You can find more about Dr. Susan Hagnes's work and her lab at uwcem.ece.wisc or Wisconsin.edu. I'd also like to thank our collaborator Huanan Zhang in the Chemical Engineering Department, but I'd like to give a special thank you to two undergraduate researchers who are leading the way in this future work that I mentioned, where we are moving this system to a 2.45 gigahertz system. And those two undergraduates are Brissa Jackson and Sean McKellar. So thank you very much for tuning into this talk. I am thrilled to answer any questions, I believe, by email. And so I have included my email below. Thank you so much for tuning into this talk. And as you're tired of hearing, stay safe.